That is, oh, it's in the middle of it. Get out. Spoiling fun. All right, let's try this again. Can you see, is it just the presentation or is it the presenter mode? Because I have two monitors.
It's the presentation.
Sweet. All right. So what I decided to do today is modify my master's defense into a much more understandable presentation that focuses more on plastics. So a little bit about, I guess, me as my credentials, I guess. I recently finished my master's degree in marine science from James Cook University last year, and since then I've been working at the Australian Institute of Marine Science, which is their government-affiliated research organization, working as a technical officer in their microplastics facility. So my research was predominantly on microplastics, but this presentation covers plastics in general. You will see some turtle pictures because it was originally adapted from a turtle-based project, but most of it applies to any organisms that do ingest plastic. All right, so you can see on the front page all my various affiliations and my supervisors. So to start, what I wanted to do is start off the presentation by kind of going over what I'm going to be talking about. So the first thing I wanted to do is talk about the background. What are plastics? What are microplastics? And how they get from the production line into becoming pollutants. Then I wanted to talk about the direct dangers of plastics to our environment, both physical and chemical. Then the more subtle threats, which are bioagent and indirect threats, how all of this really ties in together, and what we can do to help mitigate the problems that humans cause, because humans are inherently problematic, as I've discovered. So the plastics problem. To understand the danger of plastics in the environment, we really need to understand the scope of the general plastic threat. In 2017, people produced 348 million tons of plastic across the planet. That number is actually projected to rise to 700 million tons annually by 2050. And less than 1 in 10 plastics are recycled. The remainder are incinerated or trashed or littered into the environment. Although plastic pollution in the marine environment has been pretty well documented since the 1970s, we've only actually started looking at its detrimental effects in the 21st century, so the last maybe 20, maybe 30 years. The vast majority of common plastics found in the marine environment belong to 3 types of plastic. These are polyethylene, which comes in high and low density forms. It's the very common plastic that if you think plastic, this is what you're thinking of. Your milk jugs, the things you hold, a lot of cosmetic bottles, things that hold liquids, things that hold powders are usually high density polyethylene. Polyethylene also comes in a low density form. This is your plastic bags, your bread bags, your single-use sandwich bags. They are really lightweight, they're low cost, really easy to use. You can use them for a variety of things, but they're really breakable. So you can, if you've ever like torn open a piece of soft plastic, like a sandwich bag, you can tell that it fails under just a little bit of stress. Oftentimes, low density polyethylene isn't recyclable, while high density actually is pretty commonly recycled. Together, low and high density polyethylene makes up about 38% of plastics that we produce annually. The next biggest one is polypropylene, which is used for rope and netting. It's about 24% of produced plastics, very resistant. It's very useful against water and chemicals. So you'll see this one more often in slightly heavier duty situations, like bottle caps and plastic furniture pieces. About 19% of plastics are polyvinyl chloride. This is your typical PVC pipes used in construction, vinyl floors, insulation, stuff for your roof. They can actually be very tough or very not, depending on what you add to them, but that's something I'll go into a bit later. And both polypropylene and PVC are not commonly recycled. They can be rather difficult to find recycling plants. You have to speak to your local recycler to find out if they'll actually take these. These 3 different types, or 4 if you want to be technical, make up a staggering 81% of plastics that we find in today's oceans, which is an astonishing number. Plastic pollution is generally classed into 4 categories based on measurement at the largest diameter. So you have macroplastic, mesoplastic, microplastic, and nanoplastic. So macroplastics are generally larger than 20 millimeters at their largest diameter. So this is as small as things like a credit card. Those are actually considered macroplastics. Plastic bags are macroplastics. Jugs, bottles, those kind of things. Mesoplastics are usually between 5 and 20 millimeters at their largest diameter, so usually about the size of maybe coins. Or if you cut up a credit card into a number of pieces for security purposes when you get rid of it, those would be mesoplastics. Microplastics are 5 millimeters on down to 1 micrometer. Microplastics are things like glitter and microbeads and plastic pelleting. These are really small. You can still pick them up and see them individually, but they are really hard to get out. You know, once we spill glitter, it's in your house for the rest of your life. There is no escape from glitter. Then you get nanoplastics, which are sub 1 micrometer, and those are usually so small you can barely see them or even not see them at all. Those are actually a whole other beast of a problem because nanoplastics are small enough that they can get into the cell membrane of cells and cause untold amounts of damage inside of a cell, something that larger plastics tend not to be able to do. Microplastics and plastics in general can be both primary and secondary, and what this means is primary are manufactured to be the size and shape that they exist in. So again, glitter is a primary microplastic. It's manufactured to be that size. Secondary microplastics are things that come into being from the fragmentation of larger items. So when a plastic bag shreds into tiny little confetti plastic bags, that is a secondary microplastic. Microplastics can be a variety of shapes and sizes, as can meso and macro. This includes fibers, flat discs, beads, pellets, and the most common, which is actually irregular, meaning completely random shapes and sizes. They are ubiquitous and persistent, and what this means is once they reach an area of the ocean, they are a constant problem and you cannot get them out. So plastics are difficult because they break down. You can break them down in a number of different ways. It can be physical, i.e. abrasive wave action, fragmentation, tearing it apart. They can be damaged by microorganisms. Molds, bacteria can actually contribute to the breakdown of plastics. Chemical weathering, the actual exposure of salt water to plastic increases the speed at which it breaks down. UV radiation actually damages the bonds that hold polymers together, leading to, again, enhanced breakdown. And abrasive forces like wave action can actually lead things to shatter quicker. Excuse me. So what happens is plastics will break down. They never go away. They'll just go from a large to a small to a tiny to a barely existent plastic, but they are still plastics. Anyone who tells you that biodegradable plastics are inherently better is probably lying to you, or they don't really understand what's going on, because biodegradable plastics aren't necessarily better for the environment. They simply do this breaking down process a lot faster. It doesn't change their composition, it doesn't change their threat, it simply changes how quickly they make smaller particles. So we've talked about primary and secondary microplastics, and they actually come into the environment in very different ways. Primary, particularly things in cosmetics and hygiene products, generally enter the marine environment via runoff and various wastewater. Microbeads are the most common to discuss. They are usually rinsed down the sink out of face wash into sewage and wastewater treatment systems, but are too small for standard treatment filtration because standard water treatment has a mesh of 1.5 millimeters in diameter. Sorry, guys. Because this mesh is too big, oh my goodness.
You poor thing.
We are having a good day. Sorry.
You're fine, take your time.
It's fun being sick. These plastics actually get into the ocean and bypass capture entirely. Oh my gosh. Thought I was going to be able to talk the whole time. Secondary microplastics enter the marine environment as macroplastic litter in terrestrial runoff, and they often go into uncontained landfills. Sweet mother. And then they can be carried into waterways by wind or weather events, or even fishing gear debris, which is the industry circled in the corner. That actually comprises the majority of marine litter depositing because a lot of fishing gear will simply get dropped over the side of the boat. So these can cause physiochemical damage to different organisms. Physical threats include entanglement, which inhibits motion and can lead to drowning. You can also have ingestion, which can lead to gut blockages and internal abrasions. So if you've ever eaten chips, or I suppose they might be crisps, I'm not sure what your technical term is, but if you've ever eaten something that's kind of crunchy, but haven't finished chewing it, and then you swallow and it hurts your throat on the way down, you're actually causing internal abrasions because your food item is a little bit too sharp. With plastic, you actually cause that problem because plastics don't break down via digestive juices. They're simply not heavy duty enough to cause that kind of breakdown. So throughout your intestinal tract, you'll actually get little abrasions and scratches and damage as the plastic passes through. All right. Shape is really important regarding plastics and the damages they can cause. Microfibers are actually among the most dangerous of particle shapes. They are really easy to uptake into the cell because on one diameter, they have a really, really tiny edge. Fibers actually induce higher mortality rate than other shapes in ingestion trials because they are so easy to uptake. I hate being sick so much.
No,
oh my goodness.
Worse.
It's terrible. It's so annoying. So moving on from the worst to probably the least problematic, microbeads. They're the most well-studied because they're commercially available and they're really common and they're really consistent in polymer composition, shape, size, and color usually. Because they have a smooth surface, the likelihood of plastic-derived injury is really low and they're not likely to cause inflammation inside the body. But although they make up the vast majority of both environmental and ingested microplastics, irregular plastic particles are actually the most poorly understood. They're very complicated because they never match in shape, size, composition, even color, which can actually matter in ingestion because some organisms will only go for things that have a certain color. Limited research on irregular particles indicates that the effect of irregular particles is different than microbeads, including retention time inside the body and the possible toxicological effects or chemical damages. And they can actually be more hazardous to individual wellness than consistently shaped things like beads. Moving on to chemical threats. This section is a little bit confusing, even for me, so I tried to make it as simple as possible, but if it doesn't make sense, please feel free to let me know either now or in questions at the end. So plastic itself is by and large biochemically inert. It does not represent a major chemical threat. It doesn't cause chemical damage on its own. It isn't really capable of releasing chemicals into the environment. However, plastic is thought to serve as a vector for persistent organic pollutants in the environment. What this means is that persistent organic pollutants are compounds that naturally occur in the environment in small concentrations and very dispersed over large areas. However, many persistent organic pollutants have chemical properties which make them hydrophilic or anti-water and lipophilic or I guess it's a strange way to put it, but they really like to adhere to oil-based and fat-based products. What this means is they don't like being surrounded by water. Plastics are petroleum-based and therefore are an oil substrate. So they will actually go adsorb or stick to the surface of plastics in the environment. In a way, plastics act almost like a sponge for chemicals in the ocean. They don't absorb into the actual plastic, but rather stick on the surface. And then when they're ingested by another organism, they carry those chemicals on the surface into the body, where they then get released during the digestive process. It's kind of like if you were eating crackers, but your crackers were covered in cough syrup. And then you ate too many of them, and then you felt really sick because you're not supposed to ingest tons of cough syrup. All right. The next piece to the puzzle is phthalates, or plasticizers. These are also something that likes to exist. They aren't naturally occurring in the ocean usually, but plasticizers are used to alter the composition of plastics during production. So think glue or packaging. Glue is released from the bottle as a liquid or as a stick, etc. But it dries or it changes over time. Plasticizers are what enable those plastics to have different properties from what they would naturally have. They can make PVC very soft, they can make things very tough, they can make them resistant to temperature, etc., etc. They're useful because it makes the plastics that we use more robust, but the danger is that during the breakdown process of plastics, especially chemical weathering, etc., they can release those plastics into whatever substrate they are currently residing in. So they can either release plasticizers into the ocean or into the body of whatever organism has eaten a plastic. For example, in recent years, a study was done in Italy, and this one was on turtles, and they found several common plasticizers present in the bodies of 13 different turtle strandings, even though there's no reasonable reason that plasticizers should be inside the body of a turtle. The next thing that's a big chemical threat from plastics is heavy metals. They also have a very high affinity for plastic in the same way that persistent organic pollutants do. They like petroleum-based products. They're more likely to go stick to petroleum-based products like plastic to get away from all the water. And then they can get dumped into the body of anything that eats that plastic. For example, mercury in sea bass is something that has been studied regarding this kind of phenomenon. Feeding mercury-laced plastics to sea bass actually induces neurotoxicity and lipid oxidative damage. Basically, it's kind of just like you took food and poured tons of mercury on it and then ate it and expected nothing to go wrong. Like, it's going to cause problems. And that is exactly what happens in the environment, unbeknownst to all the animals that are there. We then have bioagent threats. So in extremely polluted areas, a sort of plastosphere has kind of formed. This is defined as a unique community of microbes which exists on the surface of plastic marine debris. This picture is a grocery bag, a regular run-of-the-mill. I went to the shops and got a grocery bag, but magnified 10,000 times under a scanning electron microscope. All these blue spots are various colonizing pathogens. Plastosphere containing debris hosts pathogenic bacteria, which is normally absent from the marine environment. For example, Vibrio species, which cause cholera, have been found in North Atlantic water samples, even though it's not supposed to be there, and it doesn't naturally occur in that environment because they were living on plastics found in that environment. Introducing pathogenic species into the marine ecosystem via these plastic vectors actually exposes organisms to novel diseases, which impacts animal and ecosystem health. This slide, even though I made it like 6 months ago, is super, super relevant right now because that's almost exactly what's happening to us in the real world. I say that like the ocean isn't the real world. On land, to people, we have now been dealt a novel disease that we don't know how to deal with through an unplanned and unregulated transfer of pathogens across species. So what we do by littering the environment with plastic is risking a kind of coronavirus pandemic in the ocean, even though it's not something we'd ever know about because we don't have that kind of monitoring stuff. We don't see the effects that we are causing by littering, not with bioagents. We also have to deal with indirect effects. Ingested plastics reduce gastric storage space and can alter feeding stimuli mechanisms, i.e., animals will feel satiated and they will stop foraging or hunting. It's kind of how people who are trying to lose weight will undergo a gastric bypass surgery. This will reduce the size of their stomach so less food feels like more, and then they eat less and subsequently lose weight. However, when plastics occupy gastric space, it reduces your total food intake for organisms that need that food. This actually leads to less fat deposition and less energy reserves because there's less fat, which then leads to an increased risk of illness and injury and a shortened lifespan and reduces capacity for reproductive efforts. So in a very, very roundabout way, plastics can actually cause long-term damage outside of every other thing we've already talked about. And what this kind of stuff we've talked about, physical, chemical, bioagent, indirect, all these different effects lead to news articles like this happening all the time. Plastic ingestion is a global issue. It happens as we speak, as we sleep, as we do not think about it. It is happening. Articles like this appear every few weeks, even sometimes every few months, in news sources all over the world. When I originally made this presentation last October, this had been posted a week before. This is actually only a few months ago now. And although there's a bunch of different plastic particles in that picture that were all found in that one turtle, if you put them all in a scale and weighed them, they wouldn't be more than 1 gram. It's a tiny, tiny by mass amount. Other notable stories like this happen all the time, and it's usually a tiny amount of plastic has led to a turtle, for example, suffering, or a fish suffering. A single piece of fishing line has been known to kill sea turtles. Just one single piece caused the intestinal tract to get scrunched up the way a loose thread ruins the arm of a sweater, except for that to their body. It is a horrifying thing to experience, and I imagine it's a really, really unpleasant way to go. But all of this occurs because humans litter plastic into the environment. So what have we learned from this talk? We've talked about how ingestion of plastic can cause physical damages, internal abrasions, and gut blockages. We've talked about chemicals and how they can adhere to the surface of plastics and then get re-released into the body or into the ocean. We've also talked about ingestion and how it can transport pathogens into the body and reduce food intake overall. Something that's really important that I hadn't actually discussed yet in this presentation is that some organisms actually go out of their way to eat plastic in the environment. It is a documented phenomenon, especially with turtles, which are my research animal, that they will go out of their way, even though it doesn't look like food in any way at all, they will actually go eat plastic and just assume it's food. Opportunistic species have this problem. They will eat pretty much anything that even slightly resembles maybe food. So we actually don't really have a way to quantify in the marine environment just how much plastic gets eaten every day by organisms. So that's a lot. It's a pretty heavy-hitting topic. It can be pretty rough to think about just the vast scope of how bad it is. But there are ways we can all help make a difference going forward. This picture on the side, also of note, is actually this bag that I have here. I have a little bag full of plastics that I used in a research project. And that picture and this bag, which has, you know, for fingers for size, is very small. That's 162 plastics in there, which is an intense amount. How we can all make a difference is starting out by educating yourself, educating others, telling them about just how bad plastics can be, and it kind of inspires people around you to want to do better. Volunteering is really important. Volunteering for outreach groups, volunteering for research initiatives, even just spending some time telling people around you, whatever helps. it all is very important. Supporting conservation initiatives is also really important, doing things like beach cleanups, taking part in outreach programs by local aquariums and local zoos is really, really useful. Using less plastic in your daily life, and that can be as simple as you have a couple choices at the shops and you pick the one that you know is fully recyclable, or going to your local market for produce instead of using the plastic wrapped bags in your grocery store. Even just not grabbing those little bags that you're supposed to hold all your vegetables in when you're going around in the stores. Even little things like that can make a huge difference. Advocating for plastic-free legislation is also something that's really important. If your local government is considering placing a tax on single-use plastics or considering banning single-use plastics, it's really important to call your representatives and tell them that that's a good thing, that's what they should be voting for, because it takes a lot of regular people to make these kind of motions happen. And donating to research. None of this presentation and none of the research that I've been able to do would have been possible had research initiatives not existed and had funding for me to do research. So my ability to even be here is because people who are not me and people just around managed to contribute either time, money, or social media presence to research. So these are my acknowledgements. AIMS, which is where I work, the Australian Institute of Marine Science. All of my research was done through my university, James Cook in Australia, and the pictures of turtles you saw in this presentation, especially in the beginning, are actually turtles that are involved in our research efforts, etc. When you're in academia, you have a lot of research and a lot of reading, so this is actually my horrifyingly large source list, and that's the end of my presentation. So hopefully it was interesting enough, and I'm happy to answer any questions you've got.
Thank you. Can I start questions?
Mm-hmm.
What is the long-term effect on the sea with the plastic?
So we actually, at this point, seawater, we don't really have too much information about the long-term effects, but we do know the long-term effects of what happens to different organisms. However, the general understanding is that the longer that we behave in a way that doesn't consider our impacts to the ocean, i.e. the longer we keep using plastic single use, the longer we keep tossing them out in the bin, the more plastic accumulates into the ocean. Already, there are approximately 6 pieces of plastic in the ocean for every human on Earth, and there are almost 8 billion people on Earth. And that number goes up exponentially as we continue to produce plastics and then fail to recycle them appropriately.
How does plastic affect the coral?
So nanoplastics are actually small enough that coral can uptake them in place of food, or in place of zooplankton, which can actually inhibit their capacity to photosynthesize and therefore reproduce and grow. Plastics can also block access to sunlight, which can be a long-term problem because corals rely on sun to photosynthesize. What else? Got blocking the sun, actual uptake. Chemical leachate from plastics can actually also be an issue. Plasticizers can actually cause damage to corals as well. That's something that I don't have specific answers for because I actually haven't done very much research on coral myself, but I can definitely go and have a chat to some of my coworkers and see who's done research in that field.
Thank you. May I ask questions about the job itself?
Oh yeah, ask away.
Is there a way of getting an apprenticeship, or is it best to go for university first? So
my recommendation when trying to get into marine research or into working anything with the ocean is to definitely start as early as possible and to go for volunteering first. The first thing I did, for example, was I volunteered with my local aquarium as an exhibit guide. So I got a marine research science, right?
Yeah.
All right, so I would definitely say, yeah, starting as young as possible. So even, you said you're 14, 15?
Yeah.
Yeah, like even in your teenage years, it's really easy to volunteer with local zoos and aquariums, and to see what is around for volunteering opportunities. It's a good way to gain experience. Um, I would definitely say university is a really important track if you want to go into marine research in particular, because it is a research intensive field and it's also a very niche kind of subject. It's not, having intense knowledge of plastics is not something, for example, that like your everyday person would have. Um, so I would definitely say uni is probably the way to go.
Thank you. What are the best courses for A levels and then university?
So I grew up in the States and we don't actually have A levels. Remind me what A levels are?
The next level from GCSE.
Okay. I'm assuming, are these grade levels? Like,
Yeah.
all right. I would and this is for like courses you can take.
Yeah.
I would say what's really important, if you want to get into marine science, biology is really important, chemistry is really important, physics cannot hurt. If you have like options for other sciences like ecology, those are also really useful, and statistics will take you a very long way.
Thank you.
Because any research you do will involve statistics, and it's so
Is
much
math,
easier when you know what's going on.
would maths be a big part as well?
The only branch of math that I have used in the last 6 years is statistics. So it depends on what you're specifically going into. If you are looking into oceanography, you're going to need to do physics, like mathematics for physics related reasons. But if you're going into biology or chemistry, you probably won't need to know anything past statistics. Like, it can't hurt. It definitely can't. But like I took calculus when I was 16, and I haven't used calculus since I took that course. So
What percentage of the job is practical and what percentage is theory?
It depends what job you're doing. So I work as a technical officer for a research lab, so I get to do a lot of lab-based work. But I would say the exciting parts of the job, quote unquote, like the things you do out in the field, are not going to be nearly as common. Last time I did something in like field work where I was actually out on the reef doing very cool things that I like to brag to my friends about was in August of last year. And before that, it was, I think I did something in August, I did something in March, and I did something the July previous. So across 2 years, I've only actually went in the field 3 times. Now that can be really variable. If you're doing a monitoring type of study, you're probably out every month doing something. But if you are doing a research project, you'll probably only be in the field as long as you need to get the data. The research beforehand, the analysis, the writing of the papers is all going to be stuff you do at home or in the lab or in an office somewhere. It's not all, sparkles and rainbows and Ocean Ramsey on Instagram. It isn't. But it's a lot more, you feel like you have a lot of a purpose when you're doing, especially in research, because you're trying to work towards learning not only for yourself, but to share with the rest of the science community. And so even like doing the digging can be fun, writing the papers can be really fun, and the satisfaction of having completed something like that, I would say, is just as fun as, getting to be out on the reef sweating while you're lugging fieldwork around.
What do you do in the lab?
So it really varies based on what project you're doing. When I did my research, it was an ingestion study. So I spent a lot of time picking plastic out of poop, which doesn't sound like a very fun thing to do, and it was very smelly, and it took me a long time. So yeah, it's not glamorous. That is the baseline. It is not a glamorous job, but it is a really fun and rewarding thing to do. And you just have to not get bothered by being down and dirty, because in any biology field, that would go for anything terrestrial, that goes for anything marine. You know, you're gonna get sweaty and dirty and salty and probably covered in animal poop, but that's what biology is.
When a project has been completed, will you then travel to another country or stay in the same country?
I'm intending to stay in Australia as long as I can for a number of reasons. I like working here. I like my life here. I have a lot of friends here. My partner's here. But I wouldn't be opposed to going elsewhere. And sometimes it can be really beneficial in marine science, the ability to get up and go elsewhere, because sometimes like the job offers are not all in the same they're not in the same spot. So having that freedom to move around is definitely really useful.
Thank you. That's brilliant. Thank you very much.
Yeah, no worries.
Perfect. So no more questions, so Luke?
No.
Perfect.
No, thank you.
Kelly, thanks so much for giving the talk as well, even despite your poor throat and cough.
I'm sorry I was coughing so much.
Oh, not at all. And thanks, Luke and Kevin, as well, for taking part.
Thank you very much for this opportunity. It's been brilliant. It's been very informative.
No worries at all.
Yeah.
Excellent. Thank you.
Okay.
Thank
Thanks,
you.
so guys. See you so.
Bye.
Cheers. Thanks.
Bye.
Bye-bye.
Bye.